But it now gives me great pleasure to introduce our chair for this evening, Dr. Valeska Ting. Valeska is a lecturer in the Department of Chemical Engineering at the University of Bath and the university's prize research fellow in smart nanomaterials. She heads the Functional Nanoporous Materials Research Group in the Department of Chemical Engineering, which is concerned with the understanding of structure-property relationships of functional nanoporous materials and their applications to problems in sustainable energies. Her research into characterization methods for porous hydrogen storage materials are awarded the UK's Parliamentary and Scientific Committee's 2013 Set for Britain Gold Medal for Engineering and the Westminster Medal, and was also recognised by the award of the Institution of Chemical Engineers 2013 Sir Frederick Warner Medal. She's involved with the RSC's Materials Chemistry Division and co-chaired and organised the 2014 Recent Appointees in Materials Science Conference on behalf of the RSC. And so with that, it gives me great pleasure to hand over to Valeska. Welcome.
Hello, everyone. I'd just like to start by thanking Carrie for that amazing introduction. So my name's Valeska, and I'm a lecturer in the Department of Chemical Engineering at the University of Bath. And it's been my privilege to work with Jemma over the last 2.5 years as her PhD supervisor and also as her master's supervisor before that, as she's been conducting her research into sustainable energies. Now, just a few words about Jemma. She has some excellent traits which make her a fantastic scientist and engineer. So, for example, she has an insatiable curiosity about the world around her, how things work. So she asks the questions, why does that happen? How does this thing operate? And she also has a scientific rigor to be able to test her hypotheses. And this means that her research will be useful to society and has the potential to be impactful for future generations. Now, the same personality traits that make Jemma a good scientist also make her a very effective scientific communicator. So that curiosity, and as well as the creativity to try and think of new ways to enthuse other people and to get sometimes very complex, abstract messages across to people of all age and education levels is something that's quite rare. And so I always love watching Jemma explain her work, and I think after seeing her talk with the exciting title about Leerdammer cheese, I hope that you will agree with me that she does her job brilliantly. I hope you'll walk away having learnt something and with the same sort of enthusiasm for science and research that she has. So it's my pleasure to introduce Miss Jemma Rowlandson. Please take the stage.
Hello, thank you. I did not pay her to say that, I promise. It's all genuine. So thank you. My name is Jemma, and as Valeska said, I'm a PhD student in the Department of Chemical Engineering at the University of Bath. And I have to say, this is actually the first sort of 40-minute lecture I've ever given, and it's also the first lecture I've ever given that has a picture of cheese on it wearing a superhero cape. You know, these things happen. Now, I'm here to you today to tell you about how you can save the world with Leerdammer cheese. But before I start talking about that, I just want to tell a little bit about why I was invited here to speak in the first place. And that's because I was in a competition called I'm a Scientist, Get Me Out of Here. Now, it isn't quite like I'm a celebrity, get me out of here. They don't like shower us in bugs and make us wade through mud. It's actually a bit like an X Factor for scientists. It's completely online competition. You've got 5 scientists and you've got school kids that can ask you any question they want about science. It can be something about your research, maybe it's something they've heard on the news, or maybe it's something they're just curious about. Whatever they want to do, they can ask it, which is absolutely fantastic. So this is the I'm a Scientist website. My zone was the water zone, and I was fortunate enough to win my zone. And each scientist gets their own little profile. This is my one. It has a bit about your research, so I was talking about running cars off of water. But it also has like a little interview section at the bottom, which goes over like your favourite food, you know, your favourite music, that kind of stuff. So it makes you seem more as a person rather than this abstract concept in a lab coat some far, far place away. But just to give you an idea of the kind of questions I was asked, you had the ones that were actually related to my research. So I had quite a few about hydrogen devices, because I'm using water. Then there were the ones which were a bit left field, so superpowered, I think, most likely. And then there are the ones that were really abstract, such as this one about quantum computing and how it relates to water purification. That one I had to Google, quite significantly. Probably took me longer to answer that question than it did to write this talk. But it's a really fun competition, and the students get a lot out of it, the scientists get a lot out of it. I mean, for the students, they get to see that we're not just some person in a lab coat, we're people, we have personalities, and actually the stuff we do, the science we're researching, is really relevant to them and can really help them in their lives. And for the scientists, I mean, it's a lot of fun. And also, it lets you look, sometimes it gives you a different perspective. A really good example of this was, I mean, I was talking about running cars off of water, you know, which could be perfect, water everywhere, right? But someone actually asked me, they were like, what about if you get an area of drought? Can you run water cars then? And I was like, actually, no, you can't. Water as a commodity is something I didn't really think about, and actually it gave me a completely different perspective on my research. And this is from, you know, a year 8 boy, I think, who was in Bath. It gave me this perspective, and it was really, really, really cool and really rewarding. So outreach, as Valeska said, has been a really big part of my PhD. In my centre, the Centre for Sustainable Chemical Technologies, which is a doctoral training centre, they actually, in our first year, they give us the resources and the training to create new activities for outreach, and we go to science fairs and things like that. And then we don't just focus on kids, we also, after our first year, we can do adult outreach as well, things like pub science, whatever we want, and that's a really, really rewarding part of what I do. It's what I absolutely love to do as well. And not only that, but through the Women's Engineering Society at Bath University, I'm also able to not only promote STEM subjects, but also I get to talk about diversity in science and engineering. I get to promote diversity, which is a really, really cool thing. So when I'm a scientist, I was talking about how you can power cars off of water, but what I was actually talking about was hydrogen. And hydrogen is the most abundant element in the entire universe. It's used in the creation of stars, and it's really, really cool. And you actually make it from water. And the idea really is that you can take your water, you can split it apart into hydrogen and oxygen, and you can use the hydrogen to power your car. And then afterwards, once it's been for your engine, that hydrogen will get converted into water again. So it's almost a completely green cycle. Water comes in, water comes out. It has the potential to be absolutely amazing. And there's another really cool thing about hydrogen, and that is rocket fuel. Hydrogen is the highest energy density chemical fuel by weight known to man. There is nothing more powerful than hydrogen. And this is why they use it to send spaceships into space. And if you can see this like orange tank at the back here, that is entirely filled with liquid hydrogen. And the best thing is, we can actually use this rocket fuel to power our cars, which would be awesome. Just to put this into perspective, if you want to drive your car from here, Royal Society of Chemistry, up to Birmingham and back again, that's a journey of about 250 miles. Now, that's probably you probably need about 24 kilograms of petrol to make that journey. But you would only need 8 kilograms of hydrogen if you burn it in an engine, or even less, 4 kilograms if you react it in a fuel cell. Now, I know what you're thinking, this is great, why aren't we doing this right now? But there is one small problem, well, not a small problem, there is a big problem with hydrogen, and that is it's a gas. And so at room temperature, room pressure, it takes up a massive space. So even though you only need 4 kilos of hydrogen to get you to Birmingham and back again, that 4 kilograms is going to take up an area of about 45 meters cubed, which in my favorite scale, the party balloon scale, is about 600 party balloons of hydrogen gas. I should also mention it's flammable and slightly explosive. No, very explosive. So to actually attach 600 party balloons of flammable explosive gas to your car and start driving around is probably not the best thing in the world to do. So we need a better way to store hydrogen. Hydrogen cars do exist at the moment. This is one such hydrogen car. This is the Honda Clarity. And at the moment, the industrial way to store hydrogen, the best way they do it, is to compress it into gas cylinders. And these are the gas cylinders of the Honda Clarity. Now, they either use 2 gas cylinders, which is stored at 350 bar. So we're stood here quite comfortably at 1 bar of pressure. 350 bar is 350 times atmospheric pressure. It's quite high pressure. Or they can use 1 hydrogen cylinder stored at 700 bar, 700 times atmospheric pressure. It's a lot of gas to put in a very small space. And this brings a lot of issues with it. The first one is that it's public perception, because not everyone is entirely comfortable with the idea of sitting above a flammable, highly explosive gas under very, very high pressure. For some strange reason. The other is that it's actually really, really expensive, because these gas cylinders, they have to be made to withstand a car crash. So they're made of really strong materials, lots of expensive composites, and they do their job very well. A lot of research and development has gone into these cylinders. There's a great video which I couldn't find that I really wanted to show you of someone actually shooting one of these cylinders with a shotgun. It's perfectly fine, not a problem. The other really expensive thing is not just the cylinder, it's also the hydrogen itself. Because to compress a gas to 700 times, to 700 times smaller, takes a lot of energy. It's really, really expensive. And when we're trying to move away from fossil fuels to use hydrogen, having to put a lot of energy in just to get our hydrogen in the first place is not, it's not really sustainable. And so if we want to use hydrogen, if we want to stop using fossil fuels, if we want to help prevent global warming, we really need a better way to store the hydrogen gas. And this is where our Leerdammer cheese comes in. Because our Leerdammer cheese can help us store hydrogen in a much cheaper way. Now, I know what you're thinking. How can Leerdammer cheese save the world? I mean, when global warming kicks in and things start heating up a little bit, won't the cheese just kind of melt and form like a gooey fondue? Yes. At this point, I should probably confess, I'm not actually talking about Leerdammer cheese, but materials that look very much like Leerdammer cheese. They're called nanoporous materials. Now, they're not yellow, and I wouldn't eat them, but just like Leerdammer cheese, these materials are full of holes, and it's these holes which give them world-saving potential. So there are a wide variety of them which you can use, like Pokemon, got to collect them all. My personal favourite is the activated carbon, which I'll come on to a bit later. And these materials are actually very, very old as well. I mean, activated carbons, for example, they've been used in ancient Egypt to filter water, and they're still used today to filter water, not only on an industrial scale, but does anyone have a Brita water filter? One of those water filters? Yeah, make water taste better. The cartridge that you put in it actually has activated carbon in it, as well as a bit of softener. So they're still used today. Yeah. Now, no matter what you use, which material you use, no matter how old it is, they all work the same way. And that is by a process called adsorption. Now, this sounds very similar to absorption, it's what a sponge does, but they're actually 2 very different processes. And actually, the best way to think about the difference between the 2 of them is to imagine that you're holding a custard pie. Now, with absorption, absorption is the process of taking something in. So like a sponge takes some water, you eat the pie, and it's great. Adsorption is the opposite. When adsorption, you still got your custard pie, but this time someone you know, and he probably doesn't like you very much, takes the pie and throws it in your face. Because adsorption is a process of molecules sticking to a surface. Now, I could tell you all about adsorption, but the best way to tell you about it is actually to demonstrate it. And so I actually have brought an experiment here with me today, but I'm going to need the help of the entire audience. I hope that's okay. Yes? Perfect. If you said no, this would have been very awkward, especially as it's on camera. So perfect. In that case, I have my lovely assistant / supervisor who's going to help me. If you can hand out these things. Bear with me one moment. Okay, now a few of you have probably guessed where this is going to go. Bear with me one moment. Look at you, sir. Not yet. Okay, so I'm going to demonstrate to you how hydrogen is stored on these materials. So has everyone got a ball? If you have, wave it in the air. Got two, got several. Ooh, great, excellent. These are your hydrogen molecules. What I'm going to ask you to do in a minute, not just yet, is on the count of 3, I'm going to ask you to hit me with your hydrogen. So, has everyone got hydrogen? Yeah, perfect. Move into the room. Safety first. So, you all ready? Oh no, my brother's right next to me. Didn't plan this out very well. Ready? Okay, we're going to have 3, 2, 1, off you go.
We're plastic.
Yep. All good? Perfect, thank you very much. Now, as you can probably see, we have adsorption. Perfect. Hey, our hydrogen, thank you. Oh, thank you. Our hydrogen has stuck well and truly to the surface of our material. Well, some of it has, some of it's still on the floor, but we'll worry about that later. So, now because when hydrogen's a gas, it kind of floats around. It doesn't like getting too close to itself. It kind of like repels. But on the surface, it's a completely different story because molecules, especially hydrogen, love to stick to surfaces. Seriously, they just be floating around in a gas, swimming around in a liquid, whatever they want to do, until they see a surface. Then it all changes. They see the surface, they can't stop themselves, they stick, just as they have done here. Now with hydrogen, it can actually pack together a lot more closely together on the surface of a material than it can in a gas. Oops. Than it can as a gas. And this means we can store a lot more hydrogen in a much smaller space. So the idea behind this is that you're going to have your Leerdammer cheese material, you're going to fill it with hydrogen, and then you can put this inside your gas cylinder. And what's going to happen is you're going to get the hydrogen absorbed to the surface of your material, so you can store the same amount of hydrogen, but at a much lower pressure, making it safer and cheaper. And hopefully making hydrogen cars a lot more viable as well. Now, if my jumper was twice as big, or your aim twice as better, but we won't go there. If my jumper was twice as big, you'd be able to store twice as much hydrogen. So surface area is really important. And our Leerdammer cheese materials are so good at storing hydrogen because they've got a massive surface area. I mean, just to put it into context, this is 1 gram of such a Leerdammer cheese-like material. This is a MOF, a metal organic framework. And just the stuff in this vial has the same surface area as half a football pitch. This is my favourite, activated carbon, another Leerdammer cheese material. Again, this is 1 gram, and again, just the stuff in this vial has a surface area of an Olympic-sized swimming pool. So they have a massive, massive surface area, and this is what makes these materials so special. Okay. Now, I said this was hydrogen. But this can actually be any molecule. It doesn't have to be hydrogen. So these materials can be used in loads of applications, not just storing hydrogen. You can use them to remove toxins from the water. Toxins will stick to the surface of the water rather than being in your water supply. Use them to capture carbon dioxide. You can even use them in battery materials. The superpower that your material has just depends on one thing: how big the holes are. Are they really small? Are they really big? With hydrogen, you actually want really, really small holes. That's because when you put hydrogen in your material, it forms a nice layer all over the place. But then you start to put more hydrogen in. And because hydrogen loves to stick to surfaces, in really small holes, where the walls are like this, the hydrogen is going to pack nice and closely together in the middle, because it's going to want to get as close to that surface as it possibly can. So you can store a lot of hydrogen in a small space. In really big holes, you have the opposite happen. Your hydrogen, again, stuff on the surface is nice and happy, it's next to a surface. Stuff in the middle, though, it can't see the surface. They're too far away. So it's just going to float around in the middle as a gas, which means it's not going to pack together as closely. So for hydrogen, Small holes, absolutely fantastic. For water, you actually have the opposite problem. In water, the toxins stick to your surface, but they're a lot bigger than our little hydrogen molecules. So if the holes are too small, they're not going to fit in them. And also, they could block them, and means your water won't be able to pass through either. So your application, when you're designing materials, you really have to have an application in mind, because if you have the wrong pore size, it's just not going to work very well. Now, I've told you all about how hydrogen needs really small pores, needs a massive surface area, but how do we know this? I mean, how do we know how big the holes are? How do we know how big our surface area is? I showed you it's half a football pitch. It's quite big. How do we measure something that you can't see? Because these holes are tiny. They're on the order of about a nanometer in diameter. A nanometer is a billionth of a meter, so you can't see them with your eyes. Now, normally when you want to see something really small, use a microscope. The smallest a microscope can see, it's probably around a micrometer. That's a millionth of a meter. But we're still 1,000 times too big to see our tiny, tiny holes. So what do we use instead? Well, we can still use microscopes. We just have to use really big ones. This is a transmission electron microscope, so it uses electrons to see rather than visible light. You can see this is me and my supervisor looking very happy in front of it. And you can also see this microscope is absolutely massive. I mean, I'm giving you an idea, about 5'7". This extended number 2 feet above where I am. So they're massive microscopes, they take on an entire room, and they're very expensive, but they do a fantastic job. So the way it works is that you have to have a very thin layer, very thin slice of your Leerdammer cheese material. You have a detector underneath, which catches your electrons, and your electrons come in from above. And it kind of works a bit like a stained glass window. Your electrons are going to be shot towards your material, and quite a lot of them are just going to hit the surface, they're not going to go through the holes. Now, just like when light hits like the outer brick of a stained glass window, it won't pass through, it gets absorbed, so it's going to appear dark. Same thing happens with our electrons. Not all the electrons are going to make it through, so that part of our image is going to appear dark. With the holes, completely different story. Electrons come in, there's nothing in their way, they go straight through to the detector, and so just like a stained glass window, the light passes straight through the glass, and you see it, and it gives us our pretty pattern. The electrons are going to go straight through, and where there are holes, it's going to be light. So this is an image. Okay, it's not as pretty as a stained glass window, but it's actually quite impressive, because these dark areas up here are where your sample is absorbing the electrons. These light areas down here is where your sample is much thinner. Now, if you can see the scale bar at the bottom, it says 2 nanometers. Now, 2 nanometers is the same diameter as a DNA helix. So that's what we're looking at. This is how small these features in our materials are. They're smaller than your own DNA, which is quite impressive. Another really cool thing about this microscopy is see these little bumps down the bottom, little balls everywhere? These are actually atoms. You're looking at carbon atoms. And so these microscopes can see atoms. That's how far down they can go. The problem with the microscopes is that we can see holes, not a problem, but we only see a very small part of our material, a really tiny, tiny part of our sample. And just because there's something there on that tiny part of our sample doesn't mean it's all over our sample. And so if we want something representative, if we want something that covers our whole sample, if we want to know the pore size everywhere, then we need a different method. And we actually have one. We use it in the lab. It's called gas adsorption. In this one, works very much the same way as adsorption. It is adsorption. You put a layer of gas on the surface of your material, and you use that to measure the surface area and the pore size. So, if we go back to our Leerdammer cheese, when we're using gas adsorption, you don't want anything on the material to start with. If there's anything there, any water, any contamination, then it's going to mess up our measurement. So first thing we do is we heat it up, we apply a vacuum, and we pull off any gas that's on the surface. Flies away. The second thing we have to do is we actually have to cool our sample right down. Very cold, minus 200 degrees, which is the same temperature as liquid nitrogen, 77 Kelvin. The reason we have to do this is because gas is actually like like that. It's like an excitable child. At room temperature, like we are now, it's whizzing around, it's really happy, it's got way too much energy. And just like some of the hydrogen down here, if it hits our sample, it's going to bounce straight off again. It's not going to stick, and And if it doesn't stick, then we can't measure it. So, but at a cold room, in a cold room, on a winter's day, you've got a lot less energy. You're not running around. All you want to do, sit down, blanket on, watch some Pokemon. And our gas is exactly the same. If you cool it right down, all it's going to do is not going to have as much energy, so it's going to go to the surface and it's going to stick and it's going to stay there, which means we can measure it. So if you imagine this is our surface of our sample, nothing on it, nice and clear, what we do is we start putting gas into it. So our gas goes in, some doesn't go onto the surface, but mostly it sticks onto our surface. We keep going, then we actually form an entire layer of gas, a single layer across our entire surface. At this point, we can measure the surface area. And it's actually quite a simple calculation. If you imagine, this football here is your gas molecule. What happens is that we know what the cross-sectional area of our gas molecule is. And if we line them up on the surface, imagine this entire thing is covered with half of our footballs. We know how many there are, we know how much we put in, we know the cross-sectional area. All we need to do is add them up, and it gives us a surface area. For pore size, it's a bit different. We have to actually fill up all our holes with gas. So if we keep going, keep putting more gas in, we start forming a second layer. Eventually, our smallest pores, called our micropores, they're going to fill. We keep going again, our medium-sized pores, our mesopores are going to fill up. And finally, our largest pores, called macropores, are going to fill with gas. And we can actually plot a graph using this. So at our lowest pressures, our small pores take up all the gas. So medium pressures, our medium-sized pores take up gas. Large pressures, our largest pores take up the gas. And this gives us a pattern. And this pattern describes basically how big our pores are. So for this one, for example, got a bit of everything. Got a bit of small pores, got a few big pores, got a few large pores. If you've only got really tiny pores in your sample, it might look something more like this. So all the gas is being taken up at low pressure and nothing really happens at higher pressures. If you've got larger pores, it might look something more like this, where you've got not much going on down here, no small pores and massive uptake at the very end. Now, this is all well and good. We can kind of describe what happens to our pore size, but a lot of the time we want a number, especially for hydrogen, because for hydrogen, our pores, they really want to be below a nanometer, below that billionth of a meter. They want to be smaller than that. So we really need a number a lot of the time. And to get this number, this is where it gets a bit more complicated. We have to start using computers and using modelling. So what our computer does is it imagines it has a pore like this, and it basically simulates what would happen if you fill that pore with gas. It will predict what that pattern would look like. So for the really small pores, it might look something like this. Increase the pore size, might look something more like this. Keep going, and the pattern will keep changing with what the computer predicts. And eventually you get a full range of them. The final thing the computer does is it takes what you've got from your experiment, and all it does is it tries to fit all of these onto your experimental pattern. And it comes up with a model. Now, as you can see, this is its model, this little dotted line here. It's not perfect, but it's not bad. And so it's actually not far off. So from that, it actually will tell you what size pores it thinks have made up your experimental pattern. So for hydrogen, you really want it all to be down this end. You want really small pore, and you want the volume of gas taken up by those pores to be really, really big. If it's all the way up this end, then they're too large. You're not going to get anything. Your hydrogen won't pack together very closely. Okay. So I've told you all about Leerdammer cheese materials and how we can measure the pore size of Leerdammer cheese materials. The final thing I'm just going to talk about is a little bit about my PhD project, about what I do. Now, I still use Leerdammer cheese, but I use activated carbon. And I really like activated carbons because they're really simple, and you can make them from almost anything. If it's got carbon in it, you can make it into an activated carbon. And actually, if you look around this room, all these books in this library, they're all perfect material, activated carbons. But I probably wouldn't be invited back. So instead of using something valuable, like the RSC books, we prefer to use something that's not valuable, waste. So I use plant waste. I use a very particular kind of plant waste. In all plants and plant cells, the plant cell walls are actually made up of these tiny, tiny little bundles. These bundles are made up of cellulose, and they're glued together by a molecule called lignin. Now, cellulose is used in paper making. It's also used to make biofuel and a variety of other very useful things. So people like to make a lot of cellulose, but it means they also make a lot of lignin. And lignin, no one really knows what to do with lignin, because all they do at the moment is they burn it to try and recover some energy. But that's actually an awful waste, because there's 40 million tons of this stuff is produced every single year. And so what I really want to do is find a better way to use it, to turn it into a high-value activated carbon. This is what lignin looks like, chemical structure. It's a bit like Lego. It's just made up of these 3 building blocks again and again and again. And the number of these in our molecule basically just depends on where you get it from. It's got a different structure from different plants. So lignin in a pine tree will be different from lignin in a grass, which will be very different from lignin, I don't know, in a hedge. They're all very different. And what I'm really trying to do is I'm taking lignin from different sources, because the structure of our lignin is different. When I turn it into a carbon, it's also going to be different. So it's going to have a different pore size, hopefully, a different shape. And that's really what I'm trying to do. I'm trying to change the size and the shape of the pores in my Leerdammer cheese. Oops. So what I do is I start with my feedstocks. I'm using hemp, flax, and rice husk. And from them, I get lignin. It comes in varying shades of brown. It's lovely. So we start with our waste, and we turn it into a char, a carbon char. Now at this point, the char doesn't have any holes in it. So we can't use it to save the world just yet. What we have to do is have to heat it up again, and this time it was to pass a gas through it, normally carbon dioxide. And as this gas travels through the material, it creates these long channels and pores, which are our holes. Oops, so that's a char. And this is our activated carbon. This is what we're after. There we go. Now, I talk a lot about energy storage and hydrogen, but one of the things I'm also really interested in is water filtration and removing toxins from the water. Now, some toxins can actually be quite tricky to remove. I've said activated carbon's used in water filtration already, and it does a very good job, but it doesn't get everything. Some pesticides, especially this one which is used in slug pellets called metaldehyde, actually get past our activated carbon. And so what I'm trying to do is I'm changing the size and the shape of the holes and my activated carbons to selectively target these tricky toxins and remove them from the water. Okay. So, Leerdammer cheese, maybe not cheese exactly, but Leerdammer cheese-like materials can actually help us save the world. Because for hydrogen, the hydrogen can pack together a lot more closely on the surface, and it can also be used in things like water filtration. And for my PhD, I'm changing the size and the shape of the holes in my Leerdammer cheese materials to target tricky toxins and save the world. Thank you very much.
Great. Thank you, Jemma. So that was a whistle-stop tour of how her research into nanoporous materials can be useful. Now we've got time for some questions. And so if you've got any questions about Jemma's research, about porous materials, about what sort of cheese she was talking about, okay, keep in mind that she's also a seasoned I'm a Scientist competitor. So you can throw out questions about space, about her hobbies. She's very good at Taylor Swift. So anything that you want to ask, this is your time. So who wants to be brave and go first? Thank you very much. Oh, wait, we have a microphone. Okay. So this is being recorded, so please wait for the microphone before you ask your questions.
Can you say a bit more about how you get from the vegetable samples to the activated carbon? The first step is solvent extraction, is it?
Of the... from the samples here. Yeah. Yes, you can actually use a variety of processes. In paper making in industry, they use what's called the craft process. So that uses a lot of nasty chemicals, which is why they're trying to move away from it. And that's the lignin that you get out is called craft lignin, and it can actually be quite nasty. It contains quite a lot of sulfur, which is when you turn it into a carbon, it's going to come off, and it's not very nice to breathe in. So really you want to be using lignin that comes from the paper industry because there's so much of it produced. But in the lab, it's much safer for me to do a slightly different process. So I actually use ethanol. All I do is I take my feedstocks, I put them in an ethanol and water solution, and I put them in a very small autoclave, very small pressure container. And I screw this up, put it in the oven at 200 degrees, and it gets up to about 20 bar of pressure. And essentially the lignin is autocatalytic, so a small amount of acid is produced, and this breaks apart the lignin into very small bits, and the lignin goes into the ethanol. And then when you get it out, you get like it's like a black gunk, and you also get a pulp. The pulp, we don't really care about, we kind of put it to one side. The black liquor, it's called, which is what we really do care about, that contains all our lignin. All we need to do when we get that is precipitate the lignin out. So we just need to make the lignin come out of the ethanol, so we just add acid, lignin comes out, we wash it, dry it, and we're done. It's actually an industrial scale process, but it's only on the pilot scale. It's quite expensive because ethanol is quite expensive to use alcohol solvents. So it's not quite industrially viable yet. Yeah.
I think Gemma's being modest as well. It's actually quite a difficult and time-consuming process, and I can attest that she spends a lot of time in the lab trying to get these lignins out of plant waste.
I tend to come out of the lab and I have brown powder on my jeans. I'm like, is it lignin? Is it hot chocolate? It's just such a debate.
Okay, have we got another question? Oh, please.
Yes. You showed a picture of the Honda FRV with two quite large gas containers. Mm-hmm. You got any idea how large the container would be using your particular material compared to the Honda FRV?
No, I'm afraid I'm not sure. I mean, my materials aren't anywhere near that stage yet. They need to be a lot bigger. Actually, the problem you've got isn't really the size, it's the weight of material that you need. Cars, you're very constricted with vehicles. You have to have something that fits into a standard car shape. All cars have the same kind of build, no matter what kind of car it is. So when you've got onboard hydrogen storage, the hydrogen tank can only take up a very defined space, and it can also only have a very defined weight. So if we start filling our tanks of our material, there's a trade-off between how much hydrogen that material can store and how heavy that tank becomes. And we're actually limited by, I'm not sure what it is, I'm afraid, but we're actually limited by how heavy our tank can be, because eventually you're just dragging around a massive, really heavy gas cylinder, and that's really not going to help your fuel economy. But as for the size of the cylinder, they need to be, I think they're about so big. They can't be any bigger than this. That's industry standard. Yeah.
Okay. Oh, we've got a question over there.
What's the ratio, or the maximum ratio of weight, by weight, to hydrogen to your substance? What's the maximum amount of hydrogen
My
you
substance?
Get in a kilogram of material? How much hydrogen can you absorb?
My substance? Not very much. Probably about 1% of hydrogen. The best materials, I think you have to correct, is it 10 weight%? Is that right? Yeah, it's about 10 weight%. Those are the best materials. But I should say that's 10 weight% at liquid nitrogen temperature. One of the big problems with adsorption in porous materials is that as soon as you heat up your sample to room temperature, your gas gets too much energy, it leaves the surface, it won't stick to the surface. So even though something's 10 weight% at liquid nitrogen temperature, you start warming up your material to anywhere near room temperature, that drops significantly to maybe 1 weight%, half a weight%. So a lot of the systems, the car systems, they're looking at using what's called, I think, cryo adsorption. So they're looking at having basically a system on there where you have your liquid nitrogen cooling your cylinder, and you also have your adsorbent in there as well. So it's a combination of the two. Yeah.
So we're driving around with cars with fridges in them.
Very expensive fridges.
Thank you.
Okay. Have we got any questions from the young people in the audience? So what about you guys at the back? Is there anything that you want to ask Jemma? We've got someone over here. Oh, thank you.
Yeah, so you had the 3 examples of the plants there that you're using to make the lignin. Obviously, you said they're all different and produce different hulls, and obviously there's thousands, if not millions, of different types of plants. How do you decide which plants you're going to use?
Those particular 3 are the ones that I have access to. What I'm really doing at the moment is we don't know if the lignin structure is going to affect the structure of our carbon. We think it will, but we don't know it. And so what I'm really trying to prove at the moment is that it will affect it. So that's why I've chosen 3 plants that are easy to come across. Flax and hemp are actually in the same plant family, so that's quite an interesting comparison as well. And I'm extracting the lignin, making them into carbons. If it turns out it does affect the structure, then that's when we can start looking at different plants, different lignins, and we can actually try and start to control the structure. If it doesn't affect the structure, that's actually quite good as well, because it means you can use any lignin from any waste source and make the carbon that you want. So there's two avenues of research there. It just depends what happens next.
Has anyone got another question? Yep, great. Down the front.
The back.
Too many people with questions. Okay, down the back first and then up the front.
You said carbon's your nanoporous material of choice.
Yes,
but
indeed.
What's the reason that you've chosen that one out of all of them?
Activated carbon. I really like activated carbons because, well, there's a lot of reasons. One of the big ones is that it is one of the only nanoporous materials that's produced on a very big industrial scale and has been for a long time, because we use it in water filtration, we use it an awful lot just separating stuff in general. So activated carbon technology is been well proven, and that's why applying a really well-known material to hydrogen storage or any other kind of adsorption application is, I think, much better than some of these newer materials, which are not only are they more expensive to make, the procedure is quite complicated as well. I mean, activated carbon, you just shove it in an oven and you heat it up, and then you pass some gas through it. It's really quite simple. A lot of the other materials, especially the really high surface area ones with sort of storing your 10% hydrogen, they're quite complicated to make, and I don't think they're ever going to be scalable. Because if you want, not necessarily it's not worth doing, but if you want something to be applied on a massive scale, you have to be able to make it on a massive scale, which I think is really, really important. So that's really why.
And we have a gentleman down the front who's got a question. I have to say, you guys are being great. I mean, in terms of expressing your questions in a good way and being curious about the topic.
Well, there's a change now. I understand that batteries and electric cars have the problem of storing as much lithium in the anode as possible. Is that an analogous problem to the one you're dealing with?
I don't know too much about batteries, but...
Sorry, was that in terms of the lithium being a scarce commodity, or is it...
No, just the amount of lithium that you can store in the battery and then is available for use.
Yes, no, yeah, it probably is. You can actually use carbon electrodes in batteries, I believe. I think one of the biggest problems they have is getting the lithium back out once it's gone in. So yeah, and a lot of, I don't know too much about the research into carbons and batteries, but I know a lot of the research into it is about pore size, also hierarchical pore structures, because your ions, not only do you need to store them in there, you need to have the right size of pore to store your lithium ions, but they have to actually be able to diffuse, sort of to move around within your battery structure as well, within your electrode structure. So I don't feel like I've really answered the question there. But it is, yeah, it's a problem.
Okay, we have someone with a question in the third row. Thank you.
I was wondering whether the technology would eventually be aimed at, say, powering a power station, providing electricity and general
hydrogen
energy supplies.
Yeah, hydrogen, certainly. There's actually, I mean, there's a big debate about hydrogen in general. I said you can make it from water, You can make it from water, but currently most of our hydrogen is actually made from fossil fuels, which is not exactly what we want. It's just not as efficient or as cheap to make hydrogen from water. And what they're trying to do now is they're looking more like a local scale hydrogen supply. So if you have like a wind turbine or a solar panel, you can create your hydrogen where you want it. So you don't have to move it around anywhere, you don't need to pump it anywhere. You can create your hydrogen where you want it in the quantities that you need it. Or a lot of the time they talk about using hydrogen as almost like a battery, almost as like a store of energy. So if you have a big problem with renewables at the moment, renewable power, means we can't store it. So what one suggestion is that you actually divert your excess renewable energy, so when the sun's shining, you've got enough energy already, you divert that to making hydrogen from water. You create your hydrogen, you store your hydrogen, and then when the sun's not shining, when there's not enough wind, when you do need more power, you release that hydrogen back into the grid and you can burn it, you can put it in a fuel cell, do whatever you want with it, and that will create energy. So hydrogen, definitely. And even then, there's room for adsorbents in there too, because with grid scale storage, size isn't really much of an issue. So we could store hydrogen underground, in which case having our adsorbent material is be a lot easier because we're not constrained by weight as much, we're not constrained by volume, so we can pack as much in there as we really want to store our hydrogen.
Okay. So sorry, we have another question there.
You've described the sources, material in your method for making the activated charcoal. How it's also used, as you said, in the water industry and also medicine, and to absorb drugs, somebody swallowed. How do they make that? How do they make that activated charcoal, and what's their feedstock for that?
I believe most activated carbons are made from coconut shells. They use waste. You can design like really cool templates to make into carbons, but they're often quite expensive. And actually carbon is, I said the carbons were cheap. I said they were cheap. They're actually cheaper than the other nanoporous materials. They're not cheap per se. Because actually you put a lot of energy in just to turn it into a char, then you've got to put more energy in to turn it into a carbon. And then once your carbons fill up, say for water toxins or for drugs, you have to regenerate your carbon. So you have to heat it up, and this means anything stuck on your surface will leave the surface, be emitted as a gas, but you also lose some carbon, which means you need to put some more carbon back in. So they're cheaper than the other materials, but they're still not cheap. So sorry, what's the question again? I've gone off on a tangent.
What feedstock
feedstock.
The others, and how they made them.
So they have to use a waste feedstock. They have to use a cheap feedstock. They can't use anything really fancy because you just won't be able to afford it. So mostly it's waste and mostly it's coconut shells. So, yeah.
Okay.
Or wood of some description, actually.
So this is your chance. Has anyone got any last burning questions for Jemma? Oh, yes, down the back, please.
You explained how you got the hydrogen into the pores of the Leerdammer. When you want to release the hydrogen to use it as a fuel, how do you go about doing that?
You lower the pressure. It's actually quite simple. You get some stays stuck in the pore, but in general, most of your hydrogen is actually released back, which is why it's ideal really for gas cylinders, because you put a high pressure gas in, but it's not as high a pressure. You release the pressure, the hydrogen will just come out again.
Okay. I think there were a couple of questions down there. Excellent. Okay.
One of the problems that we get with catalysts is that the surface becomes poisoned and so becomes less effective. So when you're dealing with these nanoporous materials, your activated carbons, etc., do you have any problems in your experiments with the activity and the ability to carry on working being reduced with time, which you obviously want it to have as long a period of active high surface area activity as you can?
In general, no, we don't. Mainly because we don't need to, once we put our hydrogen in, the only thing we need to do to get it back out again is change the pressure. So we don't actually put the material under a lot of stress. But if you're using it for a different application, like water filtration, you're going to get stuff on the surface. So you will have to regenerate your carbon to get its surface area back up again. But for hydrogen, it's not. I don't think it's really an issue. What we've seen.
How do you alter your active carbon to filter out insecticides?
How do we alter them?
Yes.
Yes. This is where the lignin comes in. Because lignins in different plants have different structures, chances are, we haven't proved it yet, but chances are, when they're turned into carbons, the carbons are going to have different structures as well. And the next step from that is if it turns out the lignin, where we get our lignin from, does change the pore size of our carbon, the next step would be trying to control that. And so we might control it by blending different lignins, maybe blending the carbon with different things, so we can start changing our pore size. And once we can start controlling the pore size, we can start selectively targeting our pesticides.
I think there's a very patient gentleman, in that row. Sorry.
Hi, thank you for the talk. It was really good. I was wondering, how strongly does the mechanical strength of the material affect its efficiency? And when you create the activated carbon, do you have a way to control the mechanical strength of the material?
The mechanical strength of the carbons isn't so much of an issue, because when we make them, they're a powder. So in the application we use, we tend to just pack the powder up. But you can make monoliths of carbon, where you get your carbon, you get a binder, and you extrude it into a monolith. And at that point, it does matter. If your monolith is too brittle, then you're going to get carbon being released into whatever application you're doing, rather than staying in the monolith itself, which is not good, especially if you're using it for medical applications. You don't really want anything going into the body that shouldn't be there, even though it's only carbon. So for our applications, it's not such an issue, but it could be for different applications.
Okay. I think there was another question down there.
Just a follow-up to the earlier question about using activated carbon for water filtration. If it's really mainly about pore size and structure, does that mean that once you've sort of selected and sort of optimized it, you've got a kind of broad spectrum thing, or are they very specific to particular molecular structures that relate to a particular toxin?
Activated carbons and water filtration, they're quite broad spectrum. Finding your pores are big enough for the toxins to stick on and not inhibit your water flow is generally fine. Almost everything sticks to it, but some molecules don't stick to it, which is where I have issues with some of these pesticides. They won't stick to the carbon. We're not really sure why. It could be the pore shape is one that we're thinking about, because they come in different shapes. There can be cylinders, there can be slits, they could be like V-shaped pores. And I think that's got a lot to do with it, because they do stick on a very similar material to the carbons we're making, but it's meant to have a different pore shape. So that's why we're controlling not only the pore size, but the shape of the pores as well, or we're trying to control. Yeah.
Okay. Do we have any final questions? This is your last chance. She's only here tonight, so. Okay. Well, if not, so can I just say it's incredibly difficult to stand up here and not know what people are going to ask you. So I think Jemma has done a fantastic job, and I hope you'll join me in thanking her for a very informative and enthusiastic presentation. So. And could we also, well, there are two more groups of people I'd like to thank. First of all, the Royal Society of Chemistry for allowing us to hold this event and to use their space, and for their organisation. What's that?
And to throw plastic everywhere.
Oh, yep, and to let Jemma throw plastic everywhere. So, and then the second group is all of you for giving up your Thursday evenings to come and learn something new and to find out something about some recent research that's been going on. So I think you can give yourselves a pat on the back. But so can you please join me in a final round of applause for the Royal Society of Chemistry and for everyone here. Thanks. Yeah.